Okay, so we've looked at the, or beginning to look at the rules for finding derivatives, and we are using the limit definition to do this. We basically, in the last lecture, discovered the constant rule, the power rule, sum and difference rule, and the constant multiple rule, and the rule for the exponential function e to the x. Now I want to look at products and quotients. In other words, if we have a product or a quotient of two or more functions, quotient, right, meaning division, product meaning multiplication, how do we find the derivative? So for example, if I find the function y is x squared times e to the x, what is its derivative going to be? Well, we've learned already what the derivative of x squared is 2x by the power rule, right? Bring the 2 down in front, subtract 1 from the exponent, and we get 2x. And the derivative of e to the x, do you remember what that was? That was the easy one. It's just e to the x. So the idea is, if I take the derivative of y with respect to x, remember that notation, dy over dx, that's the derivative of y with respect to x. Is it just the derivative with respect to x of x squared, which is 2x, times the derivative with respect to x of e to the x, which is e to the x? Is it this? Well, the answer to that is no. Okay? With lots of exclamation points. So this is not true. And I could illustrate it with some examples. For example, think about, here's one we could do by simplifying. In other words, if I had y is equal to x squared times x cubed, right? And I, wanted to find the derivative. Well, what you would do if you wanted to find the derivative, you would simplify, because x squared times x cubed is x to the 5th power, right? And if I take the derivative using now the power rule, right, we would have dy dx is 5x to the what? Subtract 1 4th power, right? So we learned that power rule, so that we know is correct. Okay? But if I just said, could I take the derivative by multiplying the derivatives of these two functions, right? Because that's what we're saying over here. What's the derivative of 2x? What's the derivative of x squared? That's 2x, all right? What's the derivative of x cubed? That's 3x squared, right? So if I take the derivative of each one, I get this times this. Now we know the answer is this, 5x to the 4th. But what is 2x times 3x squared? Careful, 2 times 3 is what? Not 5. It's multiplying 6. X times x squared is what? X cubed, right? Take a look at that, right? These are clearly not the same thing. I know this one's correct. This one is incorrect. And therefore, what does this tell me? Here's one example among many where the power rule cannot be done by simply taking the derivative of each of the individual, product rule, cannot be done by taking the derivative of each of the individual functions. Okay? So I hope that makes sense to you. So what is the product rule? Well, here it is. If f and g are both differentiable functions, then their product is differentiable, and here's the derivative of the product. So if I have f times g of x, the derivative is f prime, the derivative of f times g of x, plus f times the derivative of g. So the bottom line idea is, this rule says, if you have a product of two functions, take the derivative of one, multiply it by the other, and add that to the derivative of the other times the first function. And that's the product rule. That's what has to work. And you can see it if I come back to this one here, x squared times x cubed. If I take the first function and take its derivative, I call that f of x is x squared, then I would get what? 2x, right? That would be the f prime of x. G of x is the second function, which is x cubed. Okay. Plus f of x was what again? X squared. So if I just say this is the function f and this is the function g. So this is x squared times g prime. So what's the derivative of g? If I'm calling g x cubed, what's that going to be? 3x squared. And what do I get here? 2x times x cubed, that's going to be equal to 2x to the fourth. X squared times 3x squared is 3x to the fourth. What is 2x to the fourth plus 3x to the fourth? That is 5x to the fourth. That gives me the correct response, right? These ones are not equal, these are equal. And so that is correct now. So this works, okay? Question is, where does it come from? I'm going to prove that to you right now using the limit definition. So if I want to find the derivative with respect to x of the product f of x times g of x, right, with the limit definition, this is the limit as h goes to 0. And so here's my function, and I need to evaluate that at x plus h first, minus evaluating it at x, all over h. So if this is some function, right, we evaluated x plus h minus evaluated x over h. This is the difference quotient, right? This is the limit definition of the derivative that we've been using, okay? Now, if you plug in again, h is 0, you're going to get 0 over 0. This is indeterminate. Now, what I'm going to do the next step is valid, but although you would probably not understand why initially we would want to do this. And so what I'm going to do is I'm going to add, subtract actually, and then add the same expression. Okay, and let me do that first. So I want to subtract from this f of x plus h times g of x. Okay, now you might say, well, you just can't subtract something, right? You definitely can't just subtract something. That changes everything. But I'm immediately going to add that same expression back. Okay, so I've sort of inserted this in here between these two, so I don't want to forget my last thing, which was negative f of x times g of x. So I've inserted in here something. If you look at this part right here that I've inserted, which you're like scratching your head going, where in the world did this come from? Why would you do that? I do hope you realize that this totals out to 0, because this is negative f of x plus f of x plus h times g of x plus f of x plus h times g of x, right? So they're opposite, so they combine to 0. So what have I actually added? I've added 0, which I can do. Now you say, why in the world would you want to add 0? And why would you want it to look like that, of all things? Well, let me explain why, and so you will see why here in a minute. Okay? What I want to do is regroup a little bit. Okay? So what I want to do is I want to take this first term, I'm going to write it up here. And I'm going to actually subtract this f of x plus h g of x, right? And then well, they're actually in the order I want them to be in. So let me do it this way. I want this to be over h, and then I'm going to add this. So basically what I've done is split up the two fractions. I'm sorry, I kind of did the wrong order to what I was supposed to do, but that's okay. I want to split this up into two fractions first of all, which I can do because notice I've got this minus this right here, plus this minus that there. I've got them over the same denominator h, so I could recombine them as one. Okay, I could recombine them as one. And again, you might be saying, where is this going? Well, up top now, notice the top of this fraction has a common factor of f of x plus h. And I'm going to pull that factor out, f of x plus h. And that's going to be leaving me up top what? G of x plus h minus g of x over h. Now, maybe you look at this, and this might look familiar. And you might begin to see why I'm doing what I'm doing here. Here I'm going to factor out a g of x. That's common to both the terms in the numerator. And that's going to leave me an f of x plus h minus f of x over h. All right. Now, some of you might be seeing where this is going. I have the limit of a sum of two things, so the limit of a sum is the sum of the limits. And then each one of these is a product, and the limit of a product is the product of the limits. And again, this is all what? Provided all of these limits exist. So first I'll say the limit as h goes to 0 of f of x plus h times the limit as h goes to 0 of g of x plus h minus g of x over h plus limit as h goes to 0 of g of x times the limit as h goes to 0 f of x plus h, running out of room here, minus f of x all over h. Okay. So again, you might not have understood why I put that in here, but kind of hindsight now, and that we're ahead here, it might make better sense why we've done this. Okay. And there's other ways to prove this product rule, but this technique is a little bit sort of mysterious, but as we proceed, we see where it comes from now. Now, let's take a look at these limits here. So there's 4 limits to talk about. I want to first talk about, well, let's start over here. What about this one? What's the limit as h goes to 0 of f of x plus h minus f of x over h? What is that thing? That thing should look familiar. That's the limit definition of the derivative of the function f. F prime of x is equal to this. Do we know this limit exists? We do. How do we know this limit exists? The reason is f and g were what? Both what type of functions? Differentiable. What's it mean to be differentiable? They're differentiable when what? The derivative exists. So that means f and g, their derivatives both exist. And so this is indeed just f prime of x. In a similar thing, then this is what? G prime of x. G is also differentiable. Okay. Now there's 2 more limits left. Let's look at this one over here. The limit as h goes to 0. Keep in mind, h is going to 0. H is changing. Does this have an h in it? G of x? No. So x is constant with respect to h. As h goes to 0, then this is just a constant, so this is just going to be g of x. Over here, can we do this? Can we plug in, right, h is equal to 0 and therefore get just f of x? Can I bring the limit inside this function, basically is what I'm asking. Can I bring the limit inside this function? And the answer is yes. If what? Do you remember when we can bring the limit in and then directly use substitution, directly let h be 0? We can do that when the function is continuous. When the function is continuous. Do we know the function f is continuous? We were told it was differentiable. Do we know it's continuous? Yes, we talked about that last time, right? In the last set of videos when we talked about the fact that if a function is differentiable, then it is continuous. The opposite's not necessarily true, right? We have a continuous function that's not differentiable, right? We have a sharp turning point, vertical tangent line, right? We talked about those things. But if the function is differentiable, it is continuous. And so this is indeed f of x. And so we get our answer, which is f of x times g prime of x plus g of x f prime of x. Okay. Now if you look at my definition above, this order is different. I've got this term back here and this term back here, and the order I'm multiplying is different if you compare it to this original answer or rule here. But that's okay, because addition is commutative, multiplication is commutative. We can do that. Okay. Well, if you didn't like this process, it's okay. We don't have to do that anymore because we now have the product rule. So let's apply it. The product rule, we do not have to rederive all this stuff I did below. We can use the product rule. So let's go right into it and let's find the true derivative of x squared times e to the x. It is not 2x e to the x. What is it now? It's the product rule, right? So it's the derivative of x squared. So notice I'm going to use this notation. We've been using this, the derivative with respect to x of x squared. I'm going to use this notation, x squared prime on the outside of the parentheses. These both mean the same thing. Take the derivative with respect to x of x squared. So I'm just going to use take the derivative of this, right? Take the derivative of the first function, right? That's the function f, and e to the x is the function g. Plus x squared times e to the x, take the derivative of that. What's the derivative of x squared? That's easy. That's the power rule. Bring the 2 down, subtract 1, I get 2 times x to the first power, or 2x. Derivative of e to the x we know is just e to the x. We proved that rule last time. And so what do we get? I get 2x e to the x plus x squared e to the x. And there's your answer. There's your answer. Right. Notice that is not 2x e to the x. It's 2x e to the x plus x squared e to the x. So it's a little more complicated. So products are a little more complicated when finding the derivatives. If you want to, you could have factored out what? An x and an e to the x here, leaving me 2 plus x. Okay. We don't have to do that though right now. You can imagine if we're trying to solve for when is the derivative, say, equal to 0 or something, then factoring would come into play. But right now I'm happy to just get to this boxed answer. Okay. No need to proceed any further than that. Let's find another example. Let's do another one here. Okay. So again, I have a product of two things. Now, I'm going to use the product rule, but I want you to think about, is this the only way we could do this problem, is with the product rule. I have the product of x squared plus 3 times x minus 5. So I'm going to take the derivative of the first one times the second plus the first times the derivative of the second. Okay. What's the derivative of x squared plus 3? Well, that's going to be 2x, derivative of x squared. So a sum, right? I can take the derivative of a sum, and it's the sum of the derivatives. So not true with products, but with sums it is. So derivative of x squared is 2x. What's the derivative of 3? 0, right? 2x plus 0, which is, of course, equal to 2x. What's the derivative of x minus 5? What's the derivative of x? It's 1, right? Derivative of x is 1. You can use the power rule, or you just realize y equals x is a line of slope 1. Derivative of 5 is 0. So I get 1 here, I get 2x here. And so if I now, I can write this out, I guess let's say 2x times x minus 5 plus x squared plus 3 times 1. Okay, there's my answer. But I might want to clean this up by distributing the 2x through, and I get 2x squared minus 10x plus x squared plus 3. And so my final answer, I can combine some like terms. 2x squared plus x squared is 3x squared minus 10x plus 3. Okay. So I'm going to leave it like that. Don't worry about trying to factor that or anything. That's the answer. Now, was this the only way I could have proceeded using the product rule? No. I could have first simplified this down. Multiply this by foiling out, right? So, or I could use this. FOIL this out. X squared times x is x cubed first. Outer x squared times negative 5, negative 5x squared. Inner plus 3x. Last 3 times negative 5, negative 15. And then what do I have? Just a simple polynomial, right? Simple polynomial. We talked about how to find the derivative here. What's the derivative of x cubed? That's 3x squared. What's the derivative of negative 5x squared? The 2 comes down. 2 times 5, 10. X to the first power, or x. And then what's the derivative of 3x? Derivative of 3x is just 3. Line of slope 3. And you can see we get the same thing. Okay. Now looking at just the amount that I wrote, it seems like this method is much easier. And I would say, yeah, so a lot of times it is better to simplify first if you can. Notice in the previous example, I could not do any simplification. You have to use the product rule to get to your result. But here, I don't have to use the product rule. I can. I might have to do a lot of work to simplify to get there, but you don't have to. You can simplify first and then take the derivative. So a lot of times, look to see if you can simplify an expression first. Okay, could you simplify an expression first? And that's what I'll do here. I mean, you could use the product rule in this case, but I'm going to simplify first. And notice in this one, these A, B, C, D, they're constants or parameters. So we're going to treat them like constants in this problem. So if I expand this thing out, what do I get? First times first, A times C, X times X, X squared. The outer is A times DX. Last is B times CX or BCX. Or the inner, the last is B times D. And so I can go right to H prime of X without the product rule, right? Now AC, right, is a constant, right? It's a constant multiple. So remember, constant multiples come out, and then we take the derivative of X squared, which is what? 2X. Okay. And again, constant multiple AD, I can pull that out. What's the derivative of X? It's 1. Same thing here. I get this, which simplifies down to 2ACX plus AD plus BC. By the way, the derivative of BD is 0. Sorry, that's a constant, right? BD is a constant. So there's a difference between a constant multiple and a constant. Okay. And by the way, just by the way, here's a little aside. If you were to, say, what is the derivative, say, with respect to x of 5x squared, you would not want to use the product rule on this, right? This is constant multiple rule, where I just take the 5 out, take the derivative of x squared. So the derivative of x squared is what? 2x. And then I multiply by 5, I get 10x. Now you could use the product rule, but the thing is, if I take the derivative of 5 times x squared, well, what's the derivative of 5? It's a constant. Derivative of any constant is 0. So that first part of our product rule, right, that first part, that f prime g of x, that first f prime would be 0, and this whole thing's gone. And you just have the constant multiple. So if f of x is a constant, the derivative is just the constant times the derivative. And so you want to make sure that you do that rather than complicate things. Okay? So constant multiple rule is very important. So we're not using product rule here. Don't need to do that. Okay, let's do one more. Let's find dy dt if y is equal to, so notice that we're differentiating now with respect to t, right? It's not dy dx, it's dy dt. Y is what? Pi e to the t square root of 5t plus 5 e to the pi. Okay, so this was a little bit complicated, and I want to take a look at the square root of 5t for a minute. How can we handle doing this? Well, be careful. This is the same as 5t to the 1/2 power. All right, 5 to the 1/2 power. Now, if I was taking the derivative just of this piece, can I just use the power rule? Can I bring the 1/2 down and subtract 1 from the 1/2 and get negative 1/2 and be done? No, because inside I don't have t, I have 5t. This is not t to the 1/2. If it was t to the 1/2, you can use power rule. But this 5t inside there changes things. But I can write this as 5 to the 1/2 times t to the 1/2. In other words, I can distribute, right? A product raised to a power, right? I can distribute the power if it's a product. Not a sum, not a difference, but a product. I can do that, product or quotients. So that's why, again, your algebra skills have to be up to par. You have to be able to do something like this without much thought. 5 to the 1/2, I'll just say, again, is square root of 5. I'm going to leave t to the 1/2 that way because that's the variable part, and if I want to take the derivative, I want to leave it in this form as opposed to putting it into the square root of t. And so that's what I'm going to change this out to. So this now is pi e to the t times this becomes square root of 5 pi e to the t times t to the 1/2. Here I just took the square root of 5 and pulled it out in front. You can do that, right? Because all I'm doing is multiplying. The order you multiply things in, again, does not matter. I just like to put the numerical coefficient up in front. Okay, so I just did a little work on simplifying before I began to take the derivative, and that's going to be important. We will a little bit later show you something very important called the chain rule, which would allow us to find the derivative of this thing using without doing the simplification. But again, even after that, after we get the chain rule, I would still say simplify this down first. Much easier to deal with. Okay, so let's find the derivative of y with respect to t. So what do we say about the square root of 5 and pi? These are constants. These are a constant multiple of this. So I can pull that constant multiple out. Right, so that's a constant multiple rule. And what do I have left? The derivative of e to the t times t to the 1/2. So what do I have to use there? That's a product rule, right? So I take the derivative of the first thing times the second plus the first times the derivative of the second. Right? So this is, again, the product rule. So as we're learning these different rules, we're going to see them, we're going to have to use sometimes multiple rules in the same sort of nesting together. All right? Got some difference rule going on, constant multiple rule, you got product rule going on, then you got power rule. They all come into play. And then I have the derivative of this thing. So what's the derivative of this thing going to be? Now, someone says e to the pi. 5 is a constant. E to the pi? Someone might say the derivative of e to the pi, isn't that just e to the pi? The derivative of e to the x is indeed e to the x. If I take the derivative with respect to x, I get e to the x. But the derivative with respect to x of e to the pi, is that e to the pi? No. E to the pi is a constant. Where is the x variable? Where is the x variable? There is none. This is a constant. You can use your calculator to approximate this number. Derivative of any constant is what? 0. This constant rule. This is the rule for the exponential function, natural exponential function. This is a constant rule. This is just a constant rule. So this is constant rule. The derivative of any constant is what? 0. 5 e to the pi is 0. Now be careful with that. So a lot of times it's very tempting. I see people do that all the time. Try and use a rule for a constant. Look and see, is there any variable in the expression at all? If there is not one, then that derivative for that term is going to be 0. Okay, so cleaning this up, the derivative e to the t with respect to t, that is e to the t. Okay, because the variable is up there. Right? It's not e squared. If it was e squared, the derivative would be 0. T to the 1/2, that's power rule. That's going to be what? Bring the 1/2 down, t to the negative 1/2. That's power rule. So we've got all these rules going on, and it is going to take you a while. You need to practice a lot of these. So this constant multiple is still here, and then we have e to the t times t to the 1/2 plus 1/2 e to the t to the negative 1/2. I pulled that 1/2 just in front of this product. And now there's some work we could do. I mean, I could certainly factor out an e to the t. I can factor out t to the 1/2, t to the negative 1/2 actually, right? Smaller exponent. I'm just going to rewrite it in without the negative exponent though. So what would this be? T to the negative 1/2. That's 1 divided by t to the 1/2, which is 1 over the square root of t. And so the final form I would write it in is e to the t times the square root of t plus 1/2 e to the t times this is e to the t up top The 2 is down here with the square root of t. Now if you want to combine this as one fraction, you can. I mean, I could have done that by factoring. But that's good for this point right now. I would like to rewrite it without the negative exponents because the original problem did not have any negative exponents in it. Okay. All right, so we've talked a lot about the product rule. We're going to do a couple more examples of using the product rule in the next example, next video rather, excuse me, and then we will, in the next video after that, we will look at the quotient rule.